Today, we're going to tackle a real classic from the world of technical interviews, the longest increasing subsequence problem. Now, this one's a fantastic example of how just a little shift in perspective can take a solution from being just okay to something truly elegant and efficient. So, let's dive right in.
So here's the big question for today. And I know, it sounds a bit weird, right? But believe it or not, a simple card game holds the secret to transforming this problem solution from kind of slow and clunky to something lightning fast. By the time we're done here, you'll see exactly how it works.
All right, first things first. Before we can solve anything, we need to be crystal clear on what the problem is actually asking. So let's break down what a longest increasing sequence, or LIS for short, really is.
Okay, so here are the two key rules you have to remember. One, the numbers have to stay in their original order. You can't just resort the array. And two, they don't have to be right next to each other. This is huge. It means we can skip elements in the original list to build our increasing sequence.
Let's make this a little more concrete. Look at this array here. A possible longest increasing subsequence is 2, 5, 7, 101. See how we skipped over 10, 9, 3, and 18? The numbers we picked are all going up, and they appear in the same relative order as they did in the original array. The length is 4. Now, you might find another one, like 2, 3, 7, 18, which also has a length of 4, but you won't find one that's longer.
All right, so how would you even begin to solve this? Well, the most natural first thought, the one that probably comes to mind for a lot of people, leads us to a classic dynamic programming solution. It's not going to be the fastest, but you know what? It builds an incredible foundation for really understanding what's going on.
So the whole idea with this DP approach is to build up our answer piece by piece. For every single number in our array, let's call it nums of I, we basically ask ourselves a question. What is the absolute longest increasing subsequence that I can make that ends with this specific number? And to figure that out, we have to look back at all the numbers that came before it. If we find a previous number that's smaller than our current one, we know, hey, we can tack our current number onto the end of that subsequence. So we just find the longest one of those we can extend, and boom, we have the LIS for our current number. Now, this approach totally works. It'll get you the right answer, but it's a bit slow, because for every single element, we might have to look back at all the elements that came before it. That gives us a time complexity of O of n squared. It's a solid start, but we can do so much better, and this is where the real magic comes in. Now, let's get to the really clever part. We're going to completely reframe the problem using this fantastic analogy from a card game called patient sorting. It's this simple visual trick that unlocks the super fast O of n log n solution. The rules are incredibly simple. Seriously, just imagine you're dealing out the numbers from our array like they're playing cards. For each number you deal, you try to place it on top of an existing pile. The one and only rule is that you have to place it on the leftmost pile where the top card is bigger than or equal to your card. If you look at all the piles and you can't find a spot for your card, no problem. You just start a brand new pile all the way on the right. That's the whole game. Okay, so after we run our example array through this little card game, this is what we're left with. We end up with 4 piles. The top card of the first pile is 2, the second is 3, then 7, then 18. And what do you notice? The total number of piles is 4. And here it is, the punchline. The entire reason we played this game was to get this one beautiful, simple result. The total number of piles you have at the very end is the exact length of the longest increasing subsequence. No coincidence. In our example, we got 4 piles, and we already knew the LIS length was 4. This is the core insight that makes the optimized algorithm work. Okay, so a card game is a great way to visualize it, but how do we actually translate this into code? Well, those piles aren't just a metaphor. They represent a very specific data structure and a clever property that we can maintain really, really efficiently. In our code, we're going to use an array, which people usually call tails, to just keep track of the top card of each pile. And here's the key idea, the invariant remaintaining. For any given length of a subsequence, we always want to know the smallest possible ending number for a subsequence of that length. Why? Because a smaller ending number gives us way more options, way more opportunities to extend that subsequence with numbers we see later. It's all about keeping your options open. And here's the payoff for all that cleverness. By using this tails array and using a binary search to figure out where each new number goes, which is super fast, we slash the time complexity from O of n squared all the way down to O of n log n. And the space complexity stays the same. So we get this massive boost in speed for basically free. Okay, here's a pro tip for your interviews, because this little detail trips a lot of people up. An interviewer might ask for the longest non-decreasing subsequence, which means numbers can be equal. The logic is just a tiny bit different. For the strict version we've been talking about, you find and replace the first pile top that's greater than or equal to your number. For non-decreasing, you replace the first one that is strictly greater. It's a subtle change in the binary search, but it's absolutely crucial to get right.
So you've got the theory, you understand both algorithms. Now let's talk about how to really nail this in an interview and avoid some of the common traps that people fall into.
Let's run through a quick list of things to watch out for. First, always be clear that a subsequence can skip elements. It's not a contiguous substring. Second, and this is a big one, remember that the tails array we built is not the final answer. It's just a tool to find the length. If they ask you to actually reconstruct the sequence, you'll need another trick like storing back pointers. And of course, always clarify up front. Do you want strictly increasing or is non-decreasing okay? Oh, and don't get thrown off by negative numbers. The logic works exactly the same.
So why does all this matter? Is it just a cool brain teaser? Not at all. This pattern shows up in some really interesting real-world problems. Think about bioinformatics, where you might use it to find common patterns in DNA strands, or in version control systems like Git. It's a fundamental pattern that's surprisingly useful. So the big takeaway here is that the LIS problem is really all about finding the longest ordered path through a set of items, and that beautiful O(n log n solution is just a masterclass in optimization. Once you really get this pattern, you start seeing it in other places. Which brings me to a final thought for you. If you can find the longest increasing sequence of 1D numbers, what happens when the items are 2D? Like finding the longest possible sequence of Russian dolls that can fit inside each other, where both their height and their width have to be increasing. But that's a story for another day.